next example, let V is equal to X, Y, Z, set of order triple, three tuples, such that X plus Y plus Z is equal to 1. That is, this is the subset of R cube. This is the subset of R cube, in which the addition of three components, that is X, Y, Z components, is equal to 1. For example, what are the elements of this set? 1, 0, 0 is the element of this set, because 1 plus 0 plus 0 is equal to 1. So 1 minus 1, 3 is also the element of this, because 1 minus 1, 3, 1 minus 1, 1, not 3, 1 minus 1, 1 is also the element of this set, because 1 minus 1 plus 1 is 1. Then 2, 3, and 2, 3, and minus 2, minus 3, and 6. What is the minus 2, minus 3 become minus 5, plus 6 is 1. So these are the elements 0, 1, 0, 0, 0, 1, also the element of this. So if the addition of X and Y and Z is 1, then it is the element of this set. So this set is the subset of R cube. So for example, 1, 2, 3 is not element of this set, because 1 plus 2 plus 3 is not equal to 1. So 1, 2, 3 is the element of R cube, 3 tuple, but it is not the element of this set V. So this is the set. Determine whether V is a vector space under usual addition and usual scalar multiplication in R3. Okay. So what are the addition? What is the addition? What is addition? Is the usual addition. Addition of the three tuples. That is, if x1, y1, z1 and x2, y2, z2, its addition is what? x1 plus x2. Three tuple again, x1 plus x2, comma y1 plus y2 plus z1 plus z2. So what is the usual addition in R3? We know that the addition of R3, this is the addition in R3. For example, this is the addition in R3. That is x, y, z plus x dash, y dash, z dash is x plus x dash, y plus y dash, z plus z dash. This is the addition in usual addition in R3. Okay. And what is the scalar multiplication in R3? Ku bar, that is k x y z is kx, ky, kz is again three tuple, right, in round bracket. So these are the usual addition and usual scalar multiplication in R3. So this the set is this subset of this R3. R3 contains all the three tuples, set of all three tuples, but this is not set of all three tuples. This V is not the set of all three tuples. This is the set of three tuples that satisfies this property, that is x plus y plus z is equal to 1. So for example, 1, 0, 0, okay, or 1 minus 1, 1 is the element of this set, okay, because their addition is 1. So this is obviously subset of R3. And what are the operations on this set? A usual addition of three tuples and usual scalar multiplication. These are the operations in R3, and these are defined on this set V. And now we have to determine whether this V is a vector space. So 0, 0, 0 does not belongs to V. So what is the property? A3 property fails for this set, because 0 plus 0 plus 0 is not equal to 1. That is, 0 vector does not exist in V, and so V is not vector space. So how we can show the set is not vector space? Just show out of the 10, one property fails for that set. Okay, so this property A3, what is the property A3 of this vector space? Definition of vector space: 0 element must exist in that set. What is the 0 element? That is, if we add that element in any element, then we have the same element. So this is the definition. And what is the property number 3A3? Existence of 0 vector. There exists 0 bar in V, called 0 vector, such that u bar plus 0 bar is u bar. And what is the 0 vector in this set V? Is the 0, 0, 0. That is, 0 bar is what? 0, 0, 0. 3 tuple 0, 0, 0. And this element does not exist in the set V, because its addition 0 plus 0 plus 0 is not equal to 1. So 0, 0, 0, that is 0 bar, does not exist in this set, and therefore property A3 fails. And therefore we say V is not vector space. 0 vector does not exist in V, and so V is not vector space. Okay. So the another property, what is about the remaining 9 properties except A3? These remaining 9 property may be satisfied or dissatisfied for this set V. But this property is not satisfied, A3 not satisfied, and therefore we say V is not vector space. In some cases, we see that the set and the two operations satisfies 5 properties and dissatisfies or fails for that set 5 property. So out of the 5 fails property, we can write any one, give it its counter example. Okay, so this is called counter example. In this set, m2 by 2 r, what is the operation addition is this, and scalar multiplication is this. Okay, ka 0 0 kb, and under this operation, so this set is not vector space because the property number m4, last property, 10th number property, fails for this set. How we can show m4 fails? By using counter example. Give counter example. So what is the, this is the element of A, v, m2 by 2 r, a 2 3 1 4, this order, this is the matrix of order 2 by 2, and 1 into A is this 2 0 0 4 because of this definition, and therefore it is not equal to A. So 1A is not equal to A for this set under these two operations, and therefore V is not vector space. So how we can show the set is not vector space? This is the example of not vector space. This is the example of not vector space. Out of the 10 properties, write any one property which fails for that set. Just write one property that which fails for that set. Then we say that the set is not vector space. So in this A3 is not satisfied for this set. Some another property out of the remaining 9 may be dissatisfied for these sets, but we have to pick up the only that property which is not satisfied for that set, which fails for that set. So just write any one property out of the fails property. Okay. So next example, V is equal to R2. So from these two examples, actually this m2 by 2r is a vector space under usual addition of two matrix and usual scalar multiplication. But if we say, but m2 by 2r, by changing the definition of scalar multiplication, what do we have the result? That V, that is m2 by 2r, is not a vector space under these two operations. So and in this the set change, the addition and usual multiplication are the operations on this set V. But set is not R3. This V set is the subset of some subset of R3. So only the operations are not responsible for the set as a vector space or not vector space. The set is also important. Here the operations are usual addition and usual scalar multiplication. That is, there is no any wrong in the operations. Usual addition and usual scalar multiplication are the true operations. Right? Okay, that is, there is no any fault in these operations, but the set is not proper. Okay, the set is wrong. The set does not satisfy the property. So in order to the set becomes a vector space, set as well as the two operations, that is the addition and scalar multiplication, all the three components are responsible. So not only the set or not only the operations responsible, all three factors are responsible. Sometimes sets is not responding the 10 property, and in some examples these operations, that is the two operations, that is usual addition and usual scalar multiplication, are not responding the 10 properties. Okay, so next example is V is equal to R2, and addition is defined like this: x1 y1 plus x2 y2 is x1 plus x2 y1 plus y2. That is the usual addition of two components, two order pairs. And kx1 y1 is kx1 comma y1. It is not kx1 y1 is not kx1 comma ky1. It is not equal to this, like this. That is, the scalar multiplication operation is not usual scalar multiplication. This is the another definition, and we have to determine whether V is a vector space with respect to these operations. So we know that R2 is a vector space under usual addition and usual scalar multiplication. This is not usual scalar multiplication, but this is the usual addition. And therefore, what is your conclusion now? The rough conclusion is that the definition of addition is the same, that is usual addition means the 5 properties out of the 10 properties of vector space, the 5 properties of addition corresponding to the operation sum or addition are satisfied for this set V. What are that? The property number C1 and the property A1, A2, A3, A4. These 5 property related to this operation addition, and this operation addition is the usual addition in R2, and therefore these 5 property obviously satisfied for this set V under these 2 operations. And the remaining 5 properties, that is what are that property C2 and M1, M2, M3, M4. These 5 property corresponds to the operation scalar multiplication, and some of these out of these 5, some of these out of 5 may be fails for this set. So this is your outlook of the answer. This is the outline of the answer. So this may be out of the 5 properties of multiplication, that is C2 and M1, M2, M3, M4. One may be fail for this set, because the scalar multiplication, definition of scalar multiplication is not usual scalar multiplication. So we focus on that 5 properties. Out of that 5 property, pick that property which fails for this set, and that property is this property, that M2 property. What is the M2 property? K plus L. What are K and L? K and L are scalars. K plus L U bar. This is the property. K plus L U bar is equal to K U bar plus L U bar. This is the M2 property. But if we show that K plus L U bar is not equal to K U bar plus L U bar, then we say the property M2 fails for this set V, and therefore we say V is not vector space. So we concentrate, and by trial and error we find out the property which fails for that set. And so we have to prove this K plus L U bar is not equal to K U bar plus L U bar. So how we can prove this? By taking the counter example, that is K and L. Take K and L, randomly take. I have take here K as 2, L as 3. Not necessary that K is 2 and L is 3. We take K as 1, L as 5, K as minus 2, L as 3 by 2. Okay, because K and L are scalars. Take any scalar. Scalar means what? The set of real number, the elements of set of real numbers. Scalar means real numbers. So we can take its negative or fractional 1 by 2, 3 by 4, or minus 3 by 4. So take K and L are any 2 real number scalars, and take U bar as the element of R2. V is equal to R2. So R2 means the order pair. Take 4, 5 as the one of the element of R2. It is not necessary that U bar take U bar as 4, 5. You can also take U bar as 1, 2, minus 2, 3, minus 2, 3 by 2. Okay. Take any order pair, okay, and its entries are what? Real number. So these 4 and 5 are not necessarily this U bar as this element 4, 5. We can also take U bar as any another element. Now we have to show K plus L U bar is not equal to K U bar plus L U bar. So find the value of K plus L U bar separately, and find the value of K U bar plus L U bar separately. Okay. So K plus L U bar is equal to what? So we have to find the value of LHS. K plus L. K is 2, L is 3, 4, 5 is the U bar. Then 2 plus 3 is 5. And 4, 5 is what? Is not equal to 20 and 25. That is 5 into 4, 5. We have to take the scalar multiplication by using this definition. It is not usual scalar multiplication. So it is what? 5 into 4, comma 5. What is K x1, y1? It's K x1, comma y1. That is just multiply this K by first component only. So 5 into 4, comma 5 by definition. Okay, this is by using definition. And is 20, comma 5. So this is the value of K plus L U bar. Now K U bar plus L U bar is what? 2 is the K value, 4, 5 is the U bar, plus L is 3, 4, 5 is the U bar. And then what is its multiplication? Is 2 into 4, comma 5 means 8, 5. And 3, 4, 5 is what? 3 into 4, 12, comma 5. Because of the definition of scalar multiplication given in the example. What is K x1, y1? Is K x1, comma y1. That is just multiply these 2 by first component only. 3 by 4, first 4, that is 12, comma 5 by definition of scalar multiplication given in example. This is not usual. This is given in the example. This definition of scalar multiplication given in the example. And what is its addition? Addition is the usual addition. This is the definition of addition. That is, take the addition of corresponding components. So 8 plus 12 is 20 and 5 plus 5 is 10 by definition of addition given in the example. And so what is LHS? Value of LHS is 20 comma 5. That is order pair 25. And what is KU bar plus LU bar is 20 comma 10. And so what is your observation? K plus LU bar is not equal to KU bar plus LU bar. And therefore V is not vector space under these two operations, because M2 property M2 fails for this set. So we can give counter example. It may be happen that this, for this example, another property, what are that? C2, M1, then M3 and M4. Out of these remaining 4 properties corresponding to scalar multiplication, maybe one of them may be dissatisfied for this set. We can also give that as a counter example. So next example, let V is equal to XYZ belongs to R3, that is set of 3 tuples, either X is 0 or Y is 0. So again, this is the subset, this V is subset of R3, contains some element of R3. What are that? Either X is 0 or Y is 0. Out of them, one of them is 0. One of them must be 0. So what are the elements of R3? 0, 2, 3 is the element of this V, not R3. What are the element of this V? 0, 2, 3. Then 2, 0, 3. Also 0, 0, 2 is also the element of this set V. So either X is 0 or Y is 0 means what? One of them must be 0. Means both may be 0. Both X and Y may be 0. That is 0, 0, 5 is also the element of set V. One of them must be 0. What are the, for example, 1, 2, 3. 1, 2, 3 is not element of V, because 1 or 2 out of the X and Y, none of them is 0. So 1, 1, 2 is not element. 1, 1, 0. 1, 1, 0 is also not the element of V, because 1, 1, 0 is not element, because out of this one X or Y is not equal to 0. Okay. So Z may or may not be 0. That is different, does not depend on the Z. So 1, 1, 0 is not also the element of this V, set V. So what are the elements of V? 2, 0, 3 or 0, 0, 5. These are the element of V. And now we have to check whether V is a vector space under or with respect to usual operation of addition and scalar multiplication. That is, operations are usual addition and usual scalar multiplication. We know that what are the operation usual scalar multiplication and usual addition. Okay. That is, and we have to determine whether this set V is a vector space under these two operations. Okay. Now, if we have to prove this set V is not vector space, we have to give the counter example for any one property out of the 10 properties. So here we take U bar as 0, 2, 3 and V bar as 3, 0, 4. These are the element of V. And then what is addition of U bar and V bar? Is 0, 2, 3 plus 3, 0, 4 is equal to, we have to take the addition of these two elements. And what is the definition of addition? Is the usual addition, that is the addition of corresponding components. 0 plus 3 is 3, 2 plus 0 is 2, and 3 plus 4 is 7. And this is not the element of V. Means V is not closed for addition, or the property C1 fails for V. Addition of every two elements of V, it does not belongs to V. We have the two elements of V, such as these two elements, such that their addition does not belongs to V, and therefore V is not vector space, because property C1 fails, or we say that V is not vector space because V is not closed for addition. Addition of each two elements of V does not belongs to V. We have two elements, such that someone say that take the element 0, 2, 3 and another element as 0, 3, 4. So if you take these two elements, suppose U bar is 0, 2, 3 and V bar as 0, 3, 4, then its addition is what? 0, 5, 7, and it belongs to V. but don't take that element, because we have to pick up the counter example. That is, we have to find the values of u bar and v bar such that these u bar and v bar are the element of v, but their addition does not belongs to v. Addition of some elements of v may be element of v, but addition of every two elements of v does not belongs to v. So this example, this counter example shows that addition of each two element of v does not belong to v. We have two elements such that their addition is not element of v. So v is not vector space. That is the property C1 fails. So from these examples, what is your observation? That if I have to prove that the set is not vector space, we have to write the counter example for any one property. For we have to show the any out of the 10 property, any one property fails for that set. And how we can show the property fails for the set? We have to give the counter example. By using counter example, we can show that the property fails for that set. So another example, let V is R3, define addition and scalar multiplication, that is plus sign dot as this. That is this is the usual addition, and this is not usual scalar multiplication. Alpha x y z is alpha x comma y comma z, and is V is a real vector space, or is a vector space. So again, the answer use like this. We have to give the answer like this. So this problem and this problem are this problem. This problem is for R2. This is the problem for R2, and now and this is the problem for R3. So again, we have to write the answer of this problem 1.17 similar to this property, similar to like this example. That is k, take k is to 2, l as 3, and take u bar as 4, 5, 6 element of R3, because we have to write the example counter example for R3, and then write find k plus l u bar and k u bar plus l u bar separately. Your observation that k plus l u bar is not equal to k u bar plus l u bar, and therefore V is not vector space. So I have to write the answer of this problem similar, same to this problem, similar to this problem. Okay, just write, take u bar as the element of, instead of R2, take element of R3. Take u bar as 4, 5, 6, okay, or 4, 5, 1, okay, or to 1, 2, 3. Take any element from R3 and show that property fails for all. Don't write this proof. It is general proof. These are the general element u bar and v bar. So don't write this proof. Okay, write that proof of the example similar to previous example. So next example, v is equal to R3, and define plus and dot as this. That is the addition like this. X plus x y z is and x dash y dash z dash is x plus x dash y plus y dash z plus z dash, and alpha x y z is alpha x comma y comma z. And again, the addition is usual addition, but the scalar multiplication is not usual scalar multiplication. And so the property of scalar multiplication, 5 property, out of the 5 property, one of them maybe fails for the same. So again, the same example like this. This is the same example. So how we can write the proof? Don't write this, that the property which are satisfied for the set. Don't write that property. Only write the property that dissatisfied, fails for that set. Okay. So what is the property? This property fails for this set. Alpha plus beta u bar is not equal to alpha u bar plus beta u bar. M2 fails for this set. So how can show M2 fails for this set? We can show by using counter example. Don't write this proof. Take alpha beta, that is KL and u bar as particular element. So this proof is also this proof is also true, useful, but by taking counter example, we can easily give this property fails for this set. Okay, so don't write this proof, write a counter example. Okay, so similar to this example, V is R3, U is x y z, V is x dash y dash z dash, and alpha is the element. We have to define. So addition is the usual addition, but scalar multiplication like this, alpha into u bar is 0, 0, 0, and therefore the operation scalar multiplication is not usual scalar multiplication. And in this example, one u bar is not equal to u bar. For any u bar belong not equal to 0. That is, take counter example. Suppose u bar is take 1, 2, 3, and then 1 into u bar is what? 0, 0, 0. because 1 into u bar is 0 0 0. And what is u bar? U bar is 1 2 3. So 1 into u bar is 0 0 0, and u bar is 1 2 3, and these two are not equal, and therefore M4 property is not satisfied for this set, and therefore V is equal to R3 is not vector space. So give the counter example. So how you can show this? Take u bar as 1 2 3 belongs to R3, and then 1 into u bar is 0 0 0, and it is not equal to u bar, and therefore M4 property is not satisfied, and therefore V is equal to R3 is not vector space. Similarly, the next example, V is equal to R3 for u is x y z, V is this x dash y dash z dash, and alpha is the real element, that is scalar, and the definition of addition is this, and the definition of scalar multiplication, alpha into u bar is 2 alpha x comma 2 alpha y comma 2 alpha z. That is not again usual scalar multiplication. And then the property alpha beta u bar is not equal to alpha into beta u bar. That is what is the property? Property number k l u bar is not equal to k l u bar. That is the property M3 fails. That M3 property, the property of multiplication, scalar multiplication. What is the property? K l u bar is not equal to this property. KL M3 property. KL u bar is not equal to KL u bar. So how you can show this property fails for this example? By taking example, particular values of K and L. So don't write this proof. Write the proof that take K and L as elements. K and L as numbers. So we have to show K L u bar is not equal to K L u bar. So take u bar as suppose 1 2 3. And take K and L as 2 and 1 and 2, or 2 and 3, 3 and 4, or 3 and 5. Okay, and find the value of LHS and find the value of RHS. And we say that these two are not equal, and therefore, so give the counter example like this. We have to write the proof like this, That is, take K, L, and U bar is the element of R3, and show that K, L, U bar. Also for this set, this example, 1 u bar is not equal to also u bar. 1 u bar. So what is 1 u bar? If you take u bar as 1 2 3, then 1 u bar is 2 into 1 into x, that is 1. 2 into 1 alpha is 1, and into y. So if you find 1 u bar, it is not equal to u bar. So this property also fails for this set. So give any one counter example. Show that any one out of these two property fails for this set. Don't write, no need to write both the properties that fails for the set. Okay, so give the counter example and show these. This set is not vector space. So similar example, next example, that let v is equal to x belongs to R, so that x is greater than or equal to 0. So is the subset of R actually. This V is the subset of R. That is the set of positive numbers. X is greater than or equal to 0 means what? What is this set V? V contains 0, 1, 2, 0 to all positive real numbers. And this is not vector space, because with respect to usual addition and usual multiplication, because the problem of existence of negative vector. Negative vector of, for example, if you take V2 as the element of V, then its negative -2 is not element of V, and therefore the set of positive real numbers, x greater than or equal to 0 means x belongs to R, and x is greater than or equal to 0 means this set is set of all positive real numbers, and this set is not vector space, because the existence of negative vector axiom fails. And negative of, because what is the that axiom number A4? Negative of each element must exist in the same set, but the element that this set contains only positive real numbers, and so the negative vector of each vector does not exist in V, and therefore V is not vector space. So similarly, we can see the remaining example in the next lecture.